Hi there, I'm Brent Baird. I'm from Instruments Direct, and I've probably met most of you over the years there, and for those who have not met me before, watch it. Water. What is water? Water is a transparent, an odorless, tasteless liquid. It's a compound of hydrogen and oxygen. It freezes at 32 degrees F. It boils at 212 degrees Fahrenheit. It is made up of a compound, as I said, hydrogen, 11.1, gotta look at my card, 188%, and of oxygen, 88.812% by weight. Water. The planet is covered by 70% of water. Water. 96% of the water on Earth is in the ocean, it's in the groundwater, it's in the ice caps, it's in the icebergs. Water. What would we do without water? We need water to sustain life on this planet. Mankind, for years and years, has fought and found ways to control and monitor water. We use water today as a tool. And a tool, the people in this room here are all about different types of facilities. So for this particular application, we have a manufacturing facility or a power facility. We use water to, on the intake of the facility. We use water to cool this part of this facility. We use it as a tool. Here we are, agricultural community all around Florida there. We use water to irrigate our crops. Hospitals, we've all been in hospitals. We use water for the hot water, for the cold water, for the heat, for the air conditioning. We use water as a tool inside a facility. Universities, we've got dorm rooms, we've got kitchens. We use water as a tool in a university. High-rises, condos, apartments, coliseums. We use water as a tool in all these different types of facilities. So now the question is, how much water do you use? We're going to look at a couple applications to kind of bring you up to speed, put everything in perspective of how much water we actually use. The question I ask you is, how much water does the average person use per day? Any suggestions? 35? Anybody over here? How much gallons of water do you use a day? 100 gallons a day. It makes a lot of ice cubes. Average person uses 80 to 100 gallons a day. Bingo. That's a lot of water. Gone to the grocery store, get a jug of water. How would you like to carry 100 gallons of water? Pretty hard. So in this case there, 100 gallons of water per person per day is a lot of water. Let's break it down to a few typical applications. I'm going to take a bath. How many gallons of water do we use to take a bath? Anybody over here? What do you think? Come on, Henry, have you ever taken a bath before? No? Oh. 25 gallons? Any other suggestions? 35? 35 to 50 gallons of water fill up the traditional bathtub. You've got your hot tubs and your freestanding tubs. You can use a lot more water than that. That's a lot of water. Then the old argument comes in, is it better to take a bath or a shower? Showing a shower there, the average shower is 5 gallons per minute. If you're in for 10 minutes, 50 gallons of water, the same as a bathtub. So it's all of relevance to how long you do it, how much you put in there. Now you can see why the hotels are putting in those water saving heads. It's a tremendous amount of water that can be saved. I wouldn't use it at home, but in a hotel. So there's a shower. Now, if you don't use the bathroom to wash, you've got to use the bathroom for the toilet. Everybody flushes the toilet a couple times a day. How much is in the flush? How many gallons of water is in the flush? Depends on the age of your toilet. The average toilet that you find today is about 3 gallons, and the newer toilets that don't work are 1.5 gallons. especially after night going to Taco Bell there. And then how many times do you flush it? I'm a couple flush. I like a clean bowl, then a couple after. That's a lot of water just from a toilet, all down the drain. Well, the dog usually uses the toilet as a water bowl. The dog also helps out in the kitchen from time to time. I have this argument with my wife all the time. She says, it's better to wash the dishes by hand. We're going to save water. And I'll say, use the dishwasher. We got this brand new $1,000 dishwasher that does and sings songs, does anything you can imagine. Let's use that. She says, no, it's better. What do you think? Dishwasher, washing by hands. What's better? Dishwasher? You're right. The newer efficiency dishwashers, 6 gallons. Some of the older ones, maybe 16 gallons. Washing by hand, it depends on how long you've got the water running there, but on an average, washing dishes by hand is going to take more time and use more water down the drain. So we kind of move off from the private sector into the commercial sector. And you can see from up here, the commercial segment of the industry, and the USA counts for 17% of the public water supply in all those buildings we just looked at before. So let's break it down and look at where they use water in these type of facilities. So this category, an office building, you can see over here, they're using about over 35% in their domestic and restroom. They're using, and they're cooling and heating over 25%. There's where all the water's going in most office buildings. Most people said, what water? There's someone in the restroom, and maybe you wash your hands and get a drink. They have no idea what's inside the building. A hospital can use over 35% of their water usage is attributed to domestic and restroom. Cooling and heating, 20%. Of course, they have some other unique cases there. They may have some medical equipment and things like that, but it uses a lot of water. Hotels, over 30% of their water is used in the domestic and restroom. Cooling and heating, probably a little bit more than 10%. That's a lot of water. Restaurants, well, it depends on the kind of restaurant you're going. Are you going to Bob's Taco Bell, sitting outside on the veranda, or you're in a 4-star restaurant? Say we're sitting in a nicer restaurant. So in this case here, the kitchen is using over 51% of water in their facility. Not so much in the heating and cooling because you're sitting out in the Florida porch where you don't need any air conditioning. Educational. Educational is a very new prime category that everybody in this room is spending a lot more time doing in balancing commissioning on universities and educational because there are a lot of energy concerns. And guess what? They use a lot of water. Most of it's domestic, restroom, some cooling and heating, some laundry there. They use a lot of water. Henry.
Why is the percentage so high on the cooling and heating when most of it is recirculated?
The internet never lies, Henry. I don't know. That's a good question. That's a very good question. Very good question. And that's why you're balancers. You're there to find out the answer to that question. The industrial water usage here, over 40% domestic restroom. Their biggest other use, a lot of industrial, a lot of landscape, and of course, cooling and heating is about 10%. So the question we had, as Henry brought up, where's all the water going? Why do we need to monitor all the water? Don't we have enough water for everything possibly? Well, no. We actually have a finite amount of water on this planet. And basically, yes, it's recyclable. You know, it's the sun heats up the surface of the earth there, and all the moisture goes up to the clouds there, and then when it gets cold, it builds up, and then it rains. How's that? It rains down onto the groundwater and back through the whole channels again. So you would think that's an endless cycle, but the rain in Spain falls mainly in the plain. What if you're not in the plain? What if you're on the west coast the last couple of years? Although California's starting to have a little rain there, they didn't have rain for a long, long time. So they had a drought condition. So although it recycles, it may not recycle, it may not rain on your parade. So you may not get the groundwater you're looking for. You may have to bring the water in to where you're at. So the cycle is there. It doesn't affect everybody the same way. So we need to monitor this for controlling purposes. So we need to start drilling this down on some of the things that you do and affect your life there. So first off, we're basically taking an inventory. So remember we looked at that manufacturing plant there at the beginning of the presentation. I'm making tomato soup today, so I have a pipe of water, I got a pipe of tomatoes, I'm gonna mix them together. Wow, what's the ratio? I need to know how much water is going through that pipe. So we need to monitor how much water is going to the pipe for an inventory purposes there. How much are you using? There'll be some controls and some regulations in your own facility there. Bottom line, why are we so interested in water? Money. It always comes back to money. Somebody gets it one way or the other. So we need to monitor water for billing purposes. So for example, I got to pay a water bill. Well, Jesus, the water's free, isn't it? Well, it's not free. As you begin to think about that, where does the water come from? Well, it comes from groundwater. They got to pump it up. It's got to go to a water treatment plant. The water treatment plant's going to send it to a pump station. The pump station is going to go through some distribution network, and then you get your water. That's what you're paying for. The water's free. It's the ride from point A to point B. So somebody's got to pay for that, so there'll be a billing meter at the front door of your building that's taking an inventory. So money plays a role. So we have to support a water distribution system, and because of that, we want to share the wealth. So say I have a condominium. Well, one guy's not going to get the bill, everybody's going to get the bill. So now we have to have sub-metering on individual units. If we have a facility, a hospital, we're going to build this lab, we're going to build the east wing, we're going to build the west wing. We need to do individual sub-metering throughout the facility there. So billing, sub-metering, and then bottom line, we have to enforce the regulations. When we don't have water, the rules get nasty. And certain parts of the country, here in Florida, for example, a lot of people rent meters from us just to monitor their wells every year. Farmer Bob's got to have a $6,000 flow meter or hire somebody to come in and test his wells once a year. So SwiftMud, the organization here that administrates that, make sure you don't take all the groundwater. If you go out west, other parts of the country there, we get calls from California all day long. A homeowner who said, if I use over 300 gallons of water today, they're going to turn my water off. And there's all kinds of regulations because they don't have the water. So the less water you have, the more regulations and more enforcements you'll have. And of course, the more tools you will need to conduct that information. So how do you determine the efficiencies of your current system that you have? And that's the biggest problem there. People really don't know what they have. I'd like to do better on using water. What do you got? You might have a city water meter in there, but I don't really know the granularity within your system, how much water you're using. So we have to go through a process which people are just finally palleting. It's called a discovery process. How much water do I have? And basically what we're going to do is we're going to map out an overall facility and look at all the different zones. We're going to look at this chiller, we're going to look at these sublines, we're going to look at each floor. We're going to map out the actual water usage through your process there. You do that all the time when you're balancing an application. This is a big picture. This is everything from soups to nuts in the building. This is total water consumption of a facility. We can monitor the hot and the cold water, the water use, and in some cases there, the temperature for a BTU calculation. Now we're looking at monitoring energy. As I mentioned before, the larger the facility, the more interested they are in water, which is a byproduct of energy, heating and cooling the water. So you have to have the tools to do this. So we're going to talk a little bit about these tools. One of the tools, of course, that I have been involved in uses sound and uses ultrasound. So Henry, quick, give us a rap song. Okay, all right, that was it. That was our musical portion of the program. Sound. Sound is a Sound wave is a pressure transmission that's via either the air or water that's at a frequency that we can normally hear. We'll call that sound. Ultrasound is at a frequency that we can't hear. It's usually above 20 kilohertz. It's a high frequency we can't hear, but he can. So there's different levels of hearing. Ever use a dog whistle? Blowing that all day long, you're not going to hear anything, but old Fido here is really going to have a hard time because it bothers him because it's a very high frequency. It's a different noise. It's got a different set of hearing than we have. So there's all different kinds of sounds. And the sound that we use for measuring flow is ultrasound. And the technology we're using today primarily is a clamp-on type device on the outside of the pipe. It sends a ultrasound through the pipe wall into the pipe, and it measures how fast the processed liquid's going. And if we know the diameter of the pipe, we can calculate the volumetric flow, or the gallons per minute. So for those who are newbies to the ultrasonic technology, we basically have two different technologies. Here's the most common one for explaining the application. We got a pipe. Flow is going from left to right, and we have two sensors. So the flow is going from left to right. We send a sound burst from this sensor downstream to this sensor, and we measure how long it took. We measure the time, transit time flow meters. Then we send a sound burst from here back to the other side of the pipe. Because it's going against the flow, it takes a longer period of time. It's like walking against a headwind. It's harder to walk against the wind than it is with the wind. So the faster the flow rate, the greater the differential of time. Not to be confused with an ultrasonic Doppler flow meter, which you don't see too much today, but long ago, a Doppler flow meter kind of works like radar. It bounces off suspended particles. People in this room don't have any suspended particles for HVAC-like applications. We use Doppler flow meters for applications with chunks of stuff in it, so we use it in sewage and sludge and oatmeal and paper stock. Transit time flow meters need no solids whatsoever, and they work in applications traditionally that are ultra pure. Deionized water, jet fuel, ammonia, liquid ammonia, potable water, drinking water, well water, glycol, sewage, but they don't work on sludge. They don't work on sludge because the beam would get blocked. That's the trade-off with an ultrasonic transit time technology. The transducer position here, you don't normally see this configuration with one in each side of the pipe because it's harder to do. So what we normally see is this configuration where the flow is going from left to right. We have two sensors on the side of the pipe there, one sounding a sound beam here and ricocheting off the back wall to the other transducer downstream. And then again, it sends a signal back here and here. Now this configuration is traditionally called the V configuration, or in some brands, the dual path. And there's other names for it as well, but it's basically two beams from here to here. And we do this configuration because we're lazy. Both transducers are on the same side of the pipe, and so we can see the installation. Traditionally, this installation method is used for pipe sizes that are about 1/2 inch up to 24 inches, traditionally. This configuration here, the single path, is more powerful. This is traditionally used on very large pipe applications, traditionally 24 inches and larger, or on applications that require this extra power. So if you have an application with that old 90-year-old crusty pipe there that you need a little extra power that it did not work here, you might want to try this configuration because it's only got one path as opposed to the two-path configuration there. So the transducer spacings are pretty much for the generic design. We'll look at frequencies later. This is the standard ultrasonic transit time transducer. Now the math of this equation is the same basic math that it has been for 50 years. So as we look at time for science, cut away from the inside the pipe there, this is a cutaway from the pipe, this is a transducer, this is a transducer. And the novelty of a transit time flow meter, it's just a big math equation. That's all it is. In the old days, you had to do the math. Now today, it kind of does it for you. So life is easier. You don't have to dial in the specific sound speed of 32-degree water with 70% glycol. This kind of does it for you. So in this case there, we have a transducer, and the crystal inside the transducer is at a specific angle. And it differs from all manufacturers in what that angle is. So you can't use a Dynasonics transducer with a GE flow meter. You can't use a Fuji flow meter with a Flexum flow meter, because everybody's got their own secret math equation there. Like, for example, the Dynasonics crystal is 33 1/3 degree. Why? It works specifically for them. Now, the reason it's at an angle here, it's got to penetrate the pipe at the least resistance at this angle. So you remember the stories with the space shuttle. The space shuttle was coming back to Earth. It had to come through the atmosphere at a specific angle. It would either bounce off the atmosphere or come at too steep and burn up. It had to have a specific trajectory. It had the least amount of resistance to come through the atmosphere. We're using the least amount of resistance coming through this pipe. So we send a signal through the pipe wall. In this case there, this pipe has a liner. We need to know the sound speed of this carbon steel pipe. Come through the pipe wall, and when it hits the processed liquid, something occurs. It's called Snell's law. You ever take a glass of water, put a straw in it, look it sideways, and the straw is kind of cockeyed, cut off? That's Snell's law. It refracts. So old Snell is factored into this equation. You need to know the sound speed of the liquid and the whole thing back up. That's a lot of math. In the old days, you had to put all that data in. Today, you put in the data, carbon steel, 12-inch pipe, water. It says, move your sensors apart 2.3 inches, put it on a pipe. So the math is still there. It's still laborious as ever, but just like your iPhone, the meter does it for you. So most of the newer brands will be able to just have drop-down menus to give you that particular information. Now, to calculate the sound speed, which the manufacturers have already done for you. So you want to do water, you go click, water, drop it down. You wanted to do oil, drop it down. You wanted to use fuel, drop it down. You wanted to use glycol, drop it down. All those things are pretty much in the memory of the flow meter. If you have a new exotic chemical, then we have to do something special. We've got charts that got thousands and thousands of sound speeds for exotic liquids that you guys would never see. But Dow Chemical developed something brand new, and we have to go backwards to calculate what the sound speed is. So in calculating the sound speed, I actually got a guy at my office there with a real big pocket protector there that likes to calculate these things out in his spare time. Sound speed has stiffness and bulk modulus and density. We have to go back. We have to break down each individual product that's in the mixture to calculate this out. And the other part is some of the newer flow meters actually compensate for this if you have different liquids. So some of the newer ultrasonic technologies that are out there, if you were to have water and 30% glycol, in the days of yore, you'd have to factor out the sound speed of the water and the sound speed of glycol and calculate the ratio. So in using that method, the speed of water was 4,900 feet per second, and the speed of glycol was 5,400 feet per second. I was going to use a 30% mixture of glycol and 70% of water, and basically this would equal 5,000 feet per second. And you'd have to go to other and type in 5,000 feet per second to get it work. Today, most of the newer flow meters, if you're plus or minus 10% of the sound speed, the autopilot on it optimizes it up or down. So 20 years ago, you're off a little bit of sound speed, it didn't work. And today, it's lazy man time. You basically, in this case there, for this flow meter, I put in water. It'd figure it out. So the technology continues to make better. It continues to make it more efficient for you to work with it. And some of the older models don't have this feature, but they're all going in this direction there. Now, as part of the sound speed, we actually have to calculate out the bulk modulus. Liquid is compressible. So I've talked to you on the phone from time to time. I'll say, you really have a hard time zeroing the flow. Most of the newer flow meters, you don't need to zero. The ancient flow meters, you need it to zero. All the new flow meters, no zero. The factory zero is just fine. The reason being, they reach such low flows. If you were to close a valve here and close a valve here and put your flow meter on here, We have a jello effect. You can't see it, but the water is actually sloshing back and forth because it's a compressible liquid. Not as much as a gas, but it is compressible. And so when we do the sound speed, we actually have to do a bulk modulus calculation. So this is a calculation that you will never have to do in your life. I've got a crazy engineer in the back room that does that for Dow chemical applications. But that's how much math. It's all a math equation, nothing more, nothing less. If you ever needed to do a zero check on an ultrasonic flow meter, you take a pipe, you fill it full of water, put a cap on it, turn it sideways. That's how you do a zeroing test on a meter. But again, as I said, all the new flow meters that are probably made in the last 5 years or so, you don't need to zero them. They're pretty much set out of the box. Now, every flow meter has certain requirements. And some requirements are, talked to a number of people at the show this week, how much straight run of pipe do I need? And if you don't have it, what's the price you pay? Generically speaking, and this is pretty much industry standard for ultrasonic technologies, I would love to have a flow profile that looked just like this. And this flow profile is faster at the center and slower near the pipe wall, this being a cutaway side of the pipe. So what we would have here is we would have these blunt and elliptical shapes from your different flow rates there. The fastest in the center. It's much like a motorboat going on the river, going down the river and weight cast out to the side. Well, gravity and friction grab a hold of the flow, depending on the type of flow and type of liquid there. It'll be slower at the pipe wall and fastest at the center. So what we want to have is the flow fastest at the center of the pipe. We call that a symmetrical flow profile. Now, regardless of its turbulent, of the shape of the parabola, and that will change based upon the flow rate, we define that as called a Reynolds number. We don't care about that. We care about, if we were to draw a center line down this pipe, the top half of pipe equals the bottom half of pipe. This scenario occurs on a water-like application when I have 10 pipe diameters after an elbow, put my sensor here, and 5 pipe diameters for another elbow, or the traditional 15 pipe diameters of straight run of pipe. That's also based upon flow rate. That's based upon 10 feet per second. Most people size a pipe and pump around 7 feet per second is the industry standard. You'll see high and low from that, but that's pretty much the case. Sometimes in a municipal application, they'll oversize the pipe. Now, if I don't have enough straight run of pipe, we call the application, you'll call it turbulent. Turbulence actually definition by Reynolds numbers. Turbulence is when you don't have enough straight run of pipe. We call it an asymmetrical flow profile. And what you have here, the flow comes up your elbow, it rolls after this elbow, and right at this point there, because this is a shorter distance, this is a longer distance, it looks like a washing machine right there. So if you were to put a sensor right there, most likely the sensor wouldn't read at all. It would fault out. Now as you move farther down the elbow there, now we get into the fuzzy areas. So here's the 10 pipe diameters. If I was to put my sensor right here, I'd have a good application. If I was to put my sensor right here, what would happen? You may have excessive turbulence and the math may not work. So you may have to profile, move your sensors to actually catch a signal. That can be problematic and that can affect the overall accuracy of your device. Well, I just happen to have a flow profile. And as we mentioned before, it's all a math equation. So before this guy even goes on the pipe, I know where the transducers go. So I've got this 10-inch carbon steel pipe. I program the meter with the pipe outside diameter, the pipe wall thickness, the pipe process liquid, and it says move your sensors apart this distance. We turn it on, boom. They all connect. Perfect. The device is 1% of rate with the factory specified. Everything's perfect. What if I don't have enough straight run of pipe? My flow profile changes. And if my flow profile changes, guess what? I may measure at one flow rate at this given point, but the flow moved. The profile moved. It went downstream or went upstream there. In that case there, I'd have to move the sensor to catch it. But that's not the spacing that the flow meter told you to move it to. Now you're out of math. You are 5:30 on a Friday afternoon. Brent, how can I just make it read something? I'll take that. That happens all the time. You guys are in the field, you're faced with difficult situations. I don't have enough straight run of pipe. What can I do? If you're point sensing, you can get away and move the sensor around prospect. If you go a 1/4 inch or 1/2 inch right to the left or something like that, in most cases there, the device is rated to be about a 1% device. But in many times there, when you have to move the sensor, you're no longer at the optimum accuracy specification. If you're not at the optimum accuracy specification, everyone asks, how far could you be off? A transit time flow meter is a math equation, so in many times if we have to go too far out of the spectrum here, we will get a fault condition and not an inaccurate condition there. So if you have too much aggressive turbulence there, it'll fault. So talking with people today, in most cases, if you have to move the sensor, it's been not an EU standard, but if you can move it anyway, right or left, and you're not moving it 4 and 5 feet there, because the thing can actually go up and down the pipe there. If you got to move it a couple inches there on a big pipe there, because sometimes the pipe's not round. You ever go see a big HD piping? It's a 36-inch pipe laying on the ground, it's like an egg. It's not even round. So the math that we use is based upon a perfect symmetrical circle. We don't have that. So if you got to move the transducer, and if you get it to read, very likely it's better than 5%. If you start to go farther apart and it faults, the accuracies, you're not going to pick it up. You're not likely to ever get a transit time flow meter that's 10 or 20% off because it won't read. It'll fault. So that's the salvation of a transit time meter. If you're too far out of the spectrum, it will work. Now what do you do with straight run of pipe limitations? If I don't have the 10 pipe, or 10 and 5, you go downstream 3/4 of the available footprint. Then you put your meter at that point, and you have to live with that. So that's the general rule of thumb, and that's elbow to elbow. If you have other major intrusions, like a butterfly valve, someone's got a temperature probe, you have to go farther down line because they create even a greater, people come all the time there, I'm going down, they drop the size down to fit a mag meter in there, or I have a DP cell in there, or I have a vortex tube in there. You got to go way down the line because it really disrupts the flow profile. And we have all different types of water. We talk to people all the time, we said, what are you measuring? They're saying, water. All right, what kind of water you got? And most of our customers have an understanding of what type of water it is, because if you're not a balancer, I know what you've got. Someone calls me up and says, I need water. The first question we says is it potable or non-potable? And the guy says, no, it's in a pipe, it's not in a pot. So right away we know we got a problem. Happens all the time. And then we'll say, because certain technologies we use that are wetted have to be certified for drinking water. They have to be NSF certified. And you don't see these, you may test them, like the city water meter that comes in the building is NSF certified. It has low lead content and you can drink from it. Some of the meters they made a few years ago were higher in lead content and you can't use them anymore. So potable water and non-potable water makes a significant difference. Now as far as an ultrasonic flow meter there, you're saying, well, I can look at this, this looks like it's potable water. Well, you've been in Florida here today. Sometimes you can see potable water looks like this. Opaqueness has nothing to do with it. Opaqueness is just all dissolved suspended solids there. There's no, nothing floating in there. It's just the colorization of the water. Now over here, this is what we call a slurry. This is a cup of mud. And a cup of mud is not really going to be very good for your particular application. So where do we use clamp-on ultrasonic flow meters? Go ahead. We use ultrasonic clamp-on flow meters for just about anything that's got water in a pipe. We use it for agriculture, we use it industrial, we use it for food, we use it for all kinds of building, commercial, residential, sub-metering, and we also measure the water to Fido's private water dish there when he's not drinking out of the toilet or out of the dishwasher. So how do we use this tool? We use this tool is a portable device, and it's also dedicated, but the people in this room primarily are going to do a couple things. You're going to balance an application, you're going to commission an application, or you're going to do a discovery process. How much water am I using? So there's all different levels there. We're going to look at some of these out-of-the-box applications coming up there. So step one, we need a device that you can walk around with. So the big technology change from years ago is you used to have these big, giant black box suitcases you had to carry around. Now they look like the size of a big, I'm dating myself, transistor radio. I talked to my daughter the other day, I need a transistor battery. She says, what's that? It's a 9-volt battery. She said, what's that? So things have evolved over time. There's no more transistor radios, no more transistor batteries there. Portable flow meters are ideal because they're spot checkers. Flow, 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 flow. Balance, balance, balance. Commission, commission. Whatever you want to do, you can put it on, you can set it up, you can collect information very promptly. Or if you want to leave it there to do a study, you can clamp it on, go away for a week and come back and collect the data. It's all non-invasive. You can add energy to the equation. You can put temperature sensors on there and measure temperature as well to calculate BTU. And what's really interesting about it is the economics of the situation. You can go out and buy a portable ultrasonic flow meter, and they range all over the place, and most of the ones that meet your requirements are about $6,000 and up to buy a portable meter. Or you go online and go click and you rent one for the week. You rent one for $600 or $700 now. So the economics for you to get a hold of this technology, there's no problem anymore. It's not money anymore. You need to find the need to use it, and the technology to use this, most of the manufacturers that make this stuff have simple startup instructions, 1 or 2 pages there. You don't need to read the 300-page manual about the diagnostic screens to monitor how much city water you have coming in or to balance a pipe. That's additional information that's not required for a typical installation. So Pete the plumber can use this technology after 5 minutes of orientation, and he can do the orientation himself. It's not a complicated beast, so the whole technology's evolved to a commodity item. And once it becomes a commodity item, there's more players in the game, the prices are more competitive, and it's user-friendly. And if it's not user-friendly, you move on to another different technology. So the portable device is a key. Now, installing the portable device, the most common question I have is, why do I have to put grease on the face of the sensor to read through the pipe? Well, I was swimming in the lake the other day, and my friend was off in the distance in his motorboat. I could hear him off in the distance there. And then I dove underwater, and all of a sudden it sounded like the motorboat was right on top of me. And that's because sound travels faster through a solid than it does through the air. So we put a little acoustic couplant, as we call it, or schmooey or grease or all kinds of things we call it, put it on a transducer. How much do you put on the transducer? The transducer is flat, the pipe is round. We just need some form of mechanical contact, and what we'll put on there is like toothpaste on a toothbrush. And the pipe itself there, to prepare the pipe, a rag or a wire brush. You don't need to take the paint off anymore. You need to remove the insulation off the pipe. You just need to get to the pipe itself, knock off anything that's loose, and you can put the device on the pipe. For a portable device, open it up, put it on, get your data, close things back up there. On a dedicated application, you can put the transducer in the pipe, cover it back up. Doesn't make any difference. You can re-insulate the application there. And there's all different flavors of grease. I'm the grease king for ultrasonic flow meters. We have 10 different flavors, just like Howard Johnson's there. The best kind of grease to use, the all-around grease, is a silicone grease. And the silicone grease will stay in the pipe under all conditions. If it's really cold, if it's really hot, and if it's really sweaty, and you'll get, when you take the insulation off the pipe on a warm day like this, you'll get moisture in the surface of the pipe. It'll work through that. Some of the water-soluble greases, which we also have, are in a little bottle, a little squirt bottle there. Your hands are clean and you can wash up when you're done, but you put on a pipe, on a wet pipe, it's gone. Put on a hot pipe, it's gone. You put on a pipe with a lot of dust or a lot of rust on the pipe there, it's not there. So it's good for certain applications, definitely short-term, long-term applications. A silicone grease is better. If you have high temperature applications, there's high temperature greases as well. Water meters. Is my current water meter accurate? It is the most common question in the world, and we get them again. We try to screen out residential people. Someone will call up about a $100 water meter. We'll get the calls all the time. I don't believe my water meter. This bill cannot be right. And the first thing I'll say is, did you have the city come out and replace your water meter? They said, yes. It was 20 years old. I told them to replace it. My bill went up. Can you imagine that? All water meters that are mechanical, the older they get, the lower they read. Don't replace your old water meters. Hint. So that's always the first key, and I can tell the water bill went up. 9 out of 10 times there, the water meter, even a new water meter, they're designed by AABC standards there. For the most part, they're right. I mean, I'm sure their computer reading could screw up every once in a while, but 9 out of 10 times, there's nothing wrong with the water meter. You very likely have a leak or something in the line if you have a major discrepancy, or there's somebody moved the decimal point when they started calculating your information there. But there's different kinds of water meters. There's a water meter on the outside of your house. Use this for smaller line sizes. This is a big boy here. This is what's in the front of this building there. This is called a compound water meter. Compound water meter is 2 water meters. We're going to look at this next, why that makes a big difference there, especially an ultrasonic flow meter in your survey work. So we have this big hotel, and I'm in the basement of a big hotel, and we got a 10-inch water line, and he wants us to monitor against a city water meter. And so we go in the basement here, we throw this on this 10-inch line there, and he basically says, I'm going to go upstairs and turn the water on, and you put your flow meter on there and measure how much we got. No problem. He comes back there and says, how much did you see? We said, we didn't see anything. He said, well, let me go do it again. Comes back down to the basement, you still don't see it. He said, I flushed it twice, how come you didn't see it? He flushed the toilet, which was 6 gallons, and a 10-inch line, which equals something like 0.001 feet per second. I can't see that. It's too low of a flow rate. And what do? Well, you use this meter. This is a city meter. This has 2 flow meters in it. It has a 10-inch turbine flow meter in it, and it has a 1-inch turbine meter flow meter sitting on the side of it. It's got a sidecar. So what happens on the real toilet flushing days, it goes for the 1-inch, and when I've got a heavier flow, it's got a flap, and it flips over to the 10-inch line. It's not a 10-inch meter. It's a 1 and a 10-inch meter. So when you go to do the flow survey there, to check the city water meter, you better make sure that if it's a compound water meter, you have to say, I have an ultrasonic flow meter and it reads down to about 1/2 foot per second. You can calculate that out based upon whatever line size it is. And some brands you can go as low as 1/10 foot per second. But you're not going to see a toilet flush in a 10-inch pipe. So something to watch for. Every flow meter has a minimum flow rate, and just like ultrasonic flow meter. Now, when we get inside the building, what's become very popular is sub-metering. We got a meter at the front door, we got a meter at the back door. And the first thing the city will say is, we don't have a meter at the back door, so whatever we put in the front door, we're going to pay you what goes out the back door. So everybody gets a bill for the gazinta and the gazada, whether you have a defined gazada. And the problem is, if you have things going inside this facility, like I am manufacturing a product and I'm reusing the water, in this case there, say maybe I've got a car wash situation and that Chevy pickup truck just drove away with 40 gallons of water in the back of it and I'm recycling it. My gazinta doesn't equal my gazada, so we have to have individual sub-metering to find out the individual zones to do this. So more and more people are asking us to monitor the effluent facilities. In some cases it's difficult because there's partially filled pipes. So there's different flow meters and different technologies for those particular applications. Submetering is the key, and submetering is where you, the balancers and the commissioning people, will see a dynamic upsurge in submetering applications. Why? Because the price of meters are going down. You can buy an ultrasonic dedicated meter for about $2,000 now. It's replacing the paddle wheel flow meters in the marketplace right now. And for that reason, you're going to have zones all over the place. You have more things to balance, more things to check, more applications for you to look at. Now, when you do your submetering, what are you going to do with the data? So if you do your testing there, you need to harvest your data. And most of the newer technologies all have data loggers on them. So you can store your records on your flow meter, and in a lot of cases, then you can download your flow meter. Some of the meters now have SD cards that you don't even use software cables. They save it as a CSV file, put it in your laptop or PC, turn in Excel, there's your data. My favorite application, this is what we've done all day after drinking all that coffee. We visited the restroom, And I have had more calls from balancers in the last couple of years on waterless urinals than I've had from anybody else. Now, you know how to balance, you know how to commission, guys, gals, it's a water meter. Water, this is what goes to this, is a water meter. Can you imagine a large facility there and every level has a restroom on it? And we just talked about a couple, 3, 4, 5 flushes, maybe 9, 10 gallons every time we flush the toilet throughout the day for hundreds of people there. That's a lot of water. So what all the things are, the rage is let's see how much water we can save. First thing is justification, because in order to install this, it's a major renovation to the building and the plumbing system there. It is not an easy retrofit. So with that in mind, it also got to be done right. There's nothing worse than a waterless urinal system that does not work. We need to monitor this. This is nothing more than a water meter application. So in this case there, the tricky part is you can put water lines that come into the system there. Based upon the line size, we need to know if we can catch that 1.5 to 3 gallons of water. And secondly, when you flush a toilet, the industrial toilets you find in a building, they're fast. Whoosh, it's gone. It's gone in a second or two. If you're logging data on your totalization, you might pick it up. If your data logger is set to take a picture once a minute, how many toilet flushes did you miss? So you have to crank everything up to measure toilet flow applications. Top of the list, a week does not go by we don't talk to somebody how to set up a toilet flow application. And Kohler's actually been in our building from time to time. It's all about water. This is a very popular application and a new regulation in many new communities, especially in the Atlanta area. We picked it up some in the Northeast and some out in the West there. Chiller, draw off, or blow down. Now, the blow down is basically the part of the system that recycles and gets all the dirty stuff out and replenishes it with new stuff at the same time. Okay, no big deal. We've been doing that for years. All of a sudden, somebody wants to measure it because it's going to the sewer. So either you, the facility, wants to measure it, or in a lot of cases, the municipality says how much you're sending to the sewer. And this can be a simple or a very difficult application, because when the blowdown comes down, it's usually in an oversized line, and it comes blurp, and the pipe's usually not full. Very difficult application to measure blurps. So what do? I've done the exotic answer and the simple answer. The simple answer is put a trap in a line. You got a full pipe. Once you put a trap in the line, just like under your sink there, raise a little end there, you still have enough head pressure to push it through. You have a full pipe then over here. So when you have a full pipe there, you can put an ultrasonic flow meter there, you can put a paddle wheel flow meter, you can put a city meter there, you can put a mag meter there, you can put all kinds of meter there. Put the trap in the line here. We just did a project on the top of the CNN building about a year ago. They didn't like the trap. We built for them exotic weir boxes with ultrasonic level sensors on top of the weir box. We made it into a wastewater application. How exotic does that? They didn't believe in the trap scenario. But so you can spend $10,000, $20,000, depending on the material, if it's PVC or carbon steel there, a little bit of plumbing will do you great. Very popular application. Put the trap on the line, you'll be the hero. And many, many, many facilities now are doing this for economic reasons, and many municipalities are requiring it as a very popular application. Well, what does this look like? My saying goes there's nothing better than a good leak. Well, this is a bad leak. Bad leak. Billions of dollars are spent every year in water losses due to leaks. The insurance industry is going gaga over it. In fact, many facilities now require flow metering primarily just for leak detection because the costs are just out of sight. We did one thing, put some meters in recently. I believe it was in DC, National Geographic building. They got hundreds of buildings there. Hopefully there was no mummies in the basement. They said a leak started about Friday afternoon and they found it Monday morning. The basement, 10 foot of water. Guess what? They put flow meters in after that. But that's a very expensive what if. And they had no leak detection. So what they're putting flow meters in primary lines and they're just tying into the billing automation system or just tying in a direct line that has a low flow cutoff or a high flow cutoff. If something's unique, someone gets a phone call, an alarm goes off there. So leak detection, primary, brand new giant application there, sponsored by the insurance industry. Energy monitoring. To monitor energy, all you need to do is add temperature to the portable flow meter or to the dedicated flow meter. As Henry's told us there, where's the water go? It's a closed loop system. It's all filled up. But all the boiler, all the blowdown, that's what it is. The filling up the blowdown and topping it off. That's a lot of water, huh? I don't think that's right. We'll have to investigate that. By adding temperature to the system here, we're looking at temperature differential. We can do this with a non-contact device there. We know we're not going to get the exact temperature inside the pipe, but the key here is temperature differential. And when you buy a system that does temperature differential, make sure they're accurate as a complete system. If you're greater than 1% temperature differential, you could be as much as 20% off on your BTU calculation. So you can't look at temperature or energy management on a haphazard method. You have to have accurate, matched temperature sensors and install them in the same location. In this case there, if I put both temperature sensors at 3 o'clock there, they're matched and they're calibrated and they're not going to have a temperature differential. If I put one on the bottom, I put one on the top, heat rises. You could have a temperature differential just when you start the game. So BTU monitoring has become very popular, and most of the meters you already have, you can add temperature to those devices there. But add what the manufacturer recommends. Don't go to a catalog house and buy a thermistor, buy a thermocouple, and make your own kit, because they're not going to be accurate enough to give you any intelligent data. Dedicated ultrasonic flow meters are primarily devices that were used in the sub-metering application. Why? Because the prices are getting so low. So you can buy a dedicated transit time flow meter for about $2,000 now. The price of a paddle wheel flow meter is about $1,500 to $1,800 without any communications. Put a hole in the pipe, service it once. The ultrasonic flow meter just became less expensive than a paddle wheel flow meter. The ultrasonic flow meters are 1% of rate. Most of the paddle wheel flow meters are 1% of full scale. They're already more accurate than that. If you're going to do an energy application, it'd be foolish to put an invasive device because you can go clamp on cheaper and more accurate. And many of the devices there, if you want to use the customer's existing RTDs, you can tie directly into the energy unit itself. There's all different brands and all different shapes and sizes there, and some of the key people are represented here.
Are there any that are wireless?
Any that are what?
Wireless?
They're just starting to come wireless now. We can add radios to it. The next generation of dedicated meters are basically going to be less expensive wireless. Right now, round one, you can get a variety of communications are Modbus, BACnet, Ethernet. We add radios to it, but the radios aren't really cheap yet. We have the first versions of the Bluetooth are just starting to come out, but Bluetooth doesn't go very far, so you got to have repeaters there. The next version out is cellular. So we've been working with cellular because then you go around the network system where you don't have to worry about screwing up anybody's existing network system there. So things are coming. Here's some of the new ones, as Henry brought up again. We're using Wi-Fi networks, and eventually they have some consumer stuff coming out that's going to go put in your house to monitor your home performance. You're going to buy it at Home Depot, and it's going to transfer with your network to the cloud. So these are going to be out in the next year or two. You're going to be able to buy them for a couple $100. And the difference is they're not accurate enough for you to use in your technology there, but this kind of tells you where the world's going, because the people behind this thing, again, are the insurance industry and not the flow meter people there. They're making it more of a commodity device there. So the technology is going, so at some point in time, you'll be able to go to the cloud to download your data or your iPhone. So we talked about flow meter technology today. We talked about where your water is today. We talked about ways to save some energy and save some water. So there's two things I want to leave with you. Is one, thank you for not pulling the fire alarm to break up my speech like the guy this morning. Appreciate that. And the second thing too, you know, next time you go and wash your face or get a drink of water, stop and think. And go back and say, where did this water come from? It came from the groundwater. It came through the groundwater, pumped up to the surface, It went to a water treatment facility. It went through some pump stations, some infrastructure, and by magic, you turn this faucet there and you get this cup of water. Aren't we fortunate to live in a time and a place to have something like this? There's other parts of the world that do not have this type of infrastructure to support that. So thank you very much for our presentation today.